All right, so halfway through this lesson, we got to this definition of logarithmic functions. What I want to do is I want you to take a look at this schematic that I drew with blocks, hearts, and circles. Okay, y is equal to a to the x. We know that this name of a is always base. Whatever base is in the exponential equation is going to be the base of the logarithm. So that's one thing to keep in mind. The other thing here is the fact that you want to think of these shapes as placeholders. So what I'm trying to show you here, and I'm going to write it like right underneath here in red, is that if you have something as a statement like this, it doesn't matter what it is. You can translate that into logarithmic form by saying, okay, log base of 1 heart that gives me the square is equal to the circle, because remember, log is synonymous with the word the exponent of, like that phrase. So the exponent is circle. Isn't that what's true here? The exponent is circle. Yes? If you take this and you break it down into its part and translate it to English. The logarithm, the exponent of the heart that gives you the square is the circle. That's exactly what this says in this equation form. Okay, so these two things are what we want to keep in mind. This is going to be important for when we get to equation solving, both logarithmic and exponential. Now, if we look at this definition, it's telling us log base a of x is the inverse of what we see up here. First thing that I want to be very, very clear about is that this x that you see here is not the same x as what you see here. What is she saying? The x that you are seeing here is what I would consider to be the answer spot. Right? The exponent of a that gives you x. So when I come over here, the exponent of a that gives you, this is the same shape that would go there. So when we talk about the inverse, it's because over here, my original x, y value now gets inverted where this x becomes this y, which is what you're seeing there. Does that make sense? Everybody clear on that? Jordan, everybody, you're all okay? Yeah? I feel like you were hibernating yesterday in a storm and you're just now coming out of it. You all look very tired today. Is that a good reading on the room right now? Yeah? Okay. Just interesting, the lack of kind of focus right now. That's a hint, get focused. Polite way of saying that. Okay, fantastic. So now, we talked yesterday about these two graphs, okay? Thank you. Here's your f of x. Thank you. Here's your g of x. Right. F of x, g of x. We're good? Yes? One person awake. Questions on that? All right, let's move on. All right, I'm going to take and erase this, and I'm going to write what we have there in blue. F of x is equal to log base a of x, which is a to the y is equal to x. Agreed? These two things mean the same thing? Everybody's good with that? Yes. Okay? I personally think it's easier to think this way. We don't really think in logarithms, we think in exponents. So this is the equation that we're graphing when we graph this right side. All right. Now, if we cover this up, because that's the other exponential equation, my domain is from 0 to infinity. My range is negative infinity to positive infinity. My x-intercept is 1, 0, and I have a vertical asymptote. All right, so this is what I went over when we started the lesson today, and that's the fact that a to the y, base to the power is equal to the answer. Notice, base to the power is equal to the answer. These two things mean the same thing. It's what I have up here also. So we can find the value of each logarithm. Tell me what 2 to what power gives me 64? Review from yesterday. 8, 6. It's not 32, correct? We know that? So 2 times 2 is 4, 8, 16, 32, 64. So that would be 6. Okay, now take a look at the next one. Log base 27 of 3. Your thought process should be 27 to what power gives me 3? What is the only way to take a base and make it smaller? You need to use roots, correct? So we're saying, all right, I have a root here. I don't know what this is. This is 27. I don't know what this is, but I know my answer has to come out to 3, correct? Okay, once again, I'm going to show you an alternate method that's going to become the norm for doing these. If I go back to what I have here, I'm going to erase this. What's 27's base? I'm going to call this x because we don't know what it is. 27 can be rewritten as base what? 3 times 3 times 3. So this 27 became this. Replace it equals 3 to the first. All I did is replace 27 with its exponential form. I now just have to solve if base 3 is equal to base 3, don't the exponents have to be equal by definition? What's 3x equal to 1? X is equal to 1/3. The cube root of 27 is 3. Yes or no? Okay, like this picture, by the way. 8 to what power gives me 16? This one's a little bit trickier. I'll write this one down. 8 to what power gives me 16? Is the answer 2? No, a lot of students will tell me the answer is 2. When we have a situation that we can't think of a power on our own, it means we're going to have to convert to common bases. Okay, same procedure as what we did here. So now 8 can be written as base 2. Call this an x. 2 to what power gives me 8? 2 to what power gives me 8? 3 times the x that's already there is equal to 2 to what power? 4. So my resulting equation is that 3x is equal to 4, x is equal to 4/3. I'm guessing most of you wouldn't have thought out that answer. So the answer here is going to be 4/3. Take a second, ask me whatever questions you want about that one. Yes, sir. All right, so thought process again. Let's analyze the thought process. Does this make sense to you, what I wrote here? Like, this is what they're asking you to do here. This means this, right? So then the next thought you have is, I can't think of an exponent for 8 that's going to give me 16. So then I have to go to a problem-solving procedure. My problem-solving says, well, let me try if I can see if I can convert them to common bases. So my 8 here became 2 to the 3rd, which is just a substitution, different numbers. And my 16 became 2 to the 4th when I went to common bases. Okay? Now I have an equation that makes sense. Base 2 to a power is equal to base 2 to a power. Doesn't that mean the exponents have to be the same if there's an equal sign between them? So that means the exponents have to have the same value. Solve the equation. Good? All right, last one. This one should be easy now. 10 to what power gives me 1 over 100? -2. Okay? We moved 10 to the denominator. It became 100, which is a square, giving you the -2. Okay. All right, you try. Go ahead and complete this section. this one, you're going to need two common base problems, the two middle ones. You're going to have to convert.
I thought we were on this yesterday, so I did this.
Well, that's good. So now you really know it, is what you're saying. I would guess most of you coming in here did not like logarithms last year.
I enjoy it.
I love logarithms, so I love teaching them, and I think that makes it easier for you all. But I like teaching them because I know,
Whatever, too.
and actually, you know, a lot of my major. You want to make some money. Not that I sit down and write my bills and do logarithm equations or anything, but you know. All right, ready for answers? Okay, I see some of you using calculators. We have two issues with calculators. Number one, half of your calculators you can go in and enter logarithms where you can put the base and the answer spot in. Half of them that you have will do that. The other half, the old operating systems do not. Therefore, to make it an even playing field for the test coming up, part of your test is no calculator, so you need to know how to do these and think them out. Just to give you a heads up, so that you don't use that as a crutch. The other reason why we want you to think them out is because I'm going to start replacing the numbers with letters, which means now you're going to go to equation solving strategies that you can't use the calculator for. So it's that same idea of like, you know, the kids using PEMDAS. You had to do it by hand even though you could just put it right in the calculator. Same thing. All right, answers. Here we go. 3, 1/4, 5/2, and -4. Which ones do you want to see?
Third.
What else? Totally free, no charge.
If it's like 1 over like the 10,000, you just count the zeros.
Yep, count the zeros. Yep.
It's okay to write the answer, just the answer, or do we have to say like actually close that?
Well, that is the answer. Log base 4 of 64 is 3. You know what I mean? So that brings me to a good point. Let's say that you were taking an SAT type problem, which this could actually happen, and it says log base 2 of 8 minus log base 3 of 27. And you're going to have a multiple choice. The answer to this would be 3 minus 3, which is 0. That would be one of the multiple choices. Yes. Substitution. You're evaluating what the logs are and substituting them and then completing the operations. That's more likely what you'll see because they want to know your skill level with logs. So they'll have different things in here, like they could have log base 3 of 1. So then this would get replaced with a 0, right? Do you understand the 0 law of logs, that kind of thing? They'll incorporate different pieces that make it multi-step. Do any of you taken the new SAT yet? Yes. Like it? Didn't like it? It's really long.
I mean,
Doesn't count against you. It's more like ACTs now, right? And it got increasingly harder as you went through. Like that was the idea of the math section, that it should be. All right, moving on. All right, so we did common logs, correct? We've already talked about all of these. Yes, find each common log. You want to write down the answers? You didn't do that? 0.778, negative 0.081, and no answer or error, no solution. Alright, we talked about this yesterday as an aside. You cannot use an exponent in order to change signs. So 10 to what power gives me negative 3? You can never convert that positive base 10 into a negative. That's why there's no solution to the log when you put it in your calculator. All right, moving on then, we have natural logs. Let's go back to here. Okay, these are the first 4 properties. Notice I've replaced out numbers with letters now. So if I say log base a of 1, it doesn't matter what a is. Anything to the what power gives me 1. 0. Okay, a can be 2, a can be 3, a can be 100. It doesn't matter what a is. Taking it to the 0 power will always generate a 1. If I look at the second problem, log base a of a. That means that these are going to be the same. Log base 2 of 2, log base 3 of 3 is asking you what is the power of a that generates just a back. The answer will always be 1. Now, part 3, log base a of a to the x says, what is the power of a that will always give me a to the x? What is the power of a that will always give me a to the x? What goes in the blank? X. All right, now, the next problem, I'm going to separate it into 2 parts, and this will make a lot of sense, I think. First of all, does that make sense to you, that the exponent has to equal the exponent? And even though I'm using the word log, and I've got bases and answers and all this stuff, at the end of the day, that says that the exponent on the left has to equal the exponent on the right. Okay? So think about it. A to what power gives me x, and a to what power gives me y, right? You're telling me that the powers are equal. So that means if they're equal, we could substitute anything in. Like if I say 2 is equal to 2. What do we know about the value of x and y then? What's always going to be true about x and y? If that relationship is true, that the exponents are always the same, what's the concluding relationship between x and y? Wouldn't x always equal y? If the powers are the same, you're always going to take a to the same power in both of them. That's the relationship. So if I look here, if log base a of x is equal to log base a of y, then x equals y. Here's another way of saying that. Cancels, cancels. Log equals log, you can unlog both sides. Some of you will see that visually a little bit better. This is the thought behind it. This is the actual work. Okay, this applies to all logarithms. It doesn't matter what it looks like. So, let's go ahead in your notes and let's graph x is equal to 2 to the y. So I make a little chart here. What do you think is going to be easier to substitute in, x's or y's? If you're doing calculations, will it be easier to feed in x's or y's? Probably y's, correct? Like if I plug in 2, 1, 0, negative 1, negative 2, what's x when y is 2? 4. Y is 1, y is 0, negative 1, negative 2, 1, 4. Well, that looks really familiar, doesn't it? It's the inverse of 2 to the x. Okay, so I made a formal table in my thing here, and I plotted them. Notice here are these points, 0, 1, 2, 1, 4, 2, 1 half, 1 quarter. So what I have here in this table, I just plotted with blue dots. Okay, here's what I want you to recognize when I look at this. Here. Okay, think of this as f of x instead of y. This is the equation. F of x is equal to 2, sorry, log base 2 is equal to f of x of x. This is this table, which is this function, log base 2 of x. Questions on that? I can tell some of you are just not there yet, misty-eyed. Please ask. How did I? Why did I?
Wait, did you say the function in blue is the inverse, or is it the same as A2?
Okay, the function in blue is this. Okay? But whenever we write functions, aren't they in y equals form? The y equals form of it is that blue logarithmic equation in the top right corner. These two things are the same thing. Yes? Kind of. All right, let's do a quick check-in. How many 3, 2, 1s? 3 is, I get it, I'm fully with you, we're good. How many are 2s and how many are like, no freaking clue? Okay, here we go. Hands up, everybody up, nice and high. 3, 2, 1s. 3, 2, 1s, 3, 2, 1s. Good, okay, awesome. Beating a dead horse for some of you then. All right. Couple rules. As you can see, we're moving down into this section of graphing logarithmic equations. Determine the domain and range. You can't take the negative. You can't take the log of a negative number. Find the vertical asymptote. So for example, what that means is that like if I have log of -3, that can't happen. That's what they mean by that. Find the vertical asymptote and find any x-intercepts. Okay, remember, in your head, you really, really need to get the idea that, oh, exponential equations look like this as a key graph. Logarithmic equations look like this as a key graph. Those are your new 2 home equations that we're adding to our list. Exponential, logarithmic, home root equations. Exponential have horizontal asymptotes. Logarithmic have vertical asymptotes. So let's start with this one. F of x is equal to log base 2 of x plus 8. Okay, well, let's follow the rules. What happens when I have parentheses x plus 8? How does it shift my graph? Left 8. So my asymptote used to be at 0, correct? Used to be at 0. Now I'm going to have a vertical asymptote at -8. So at -8, I would draw in my asymptote. My key point of 1, 0 now gets shifted left 8. So I'm going to move all the way over to here, which is -7. And nothing else changed with the graph, correct? Doesn't it look like this? What's the first question that they ask you in your list? You can only take the log of a positive number. So my domain says, what's in here? X plus 8 has to be greater than 0. X has to be greater than -8, so my domain is going to be from -8 to infinity. Does that match to my picture? Yes or no? Yes. All right, so now we're going to take a little walk down memory lane. We're going to go back about 2 units to the functions unit. What are the only 2 rules you used to have to consider when I ask you about domain algebraically? Does it have what? Denominator or even roots? Now we're adding the 3rd rule. Is it a logarithmic equation? Logarithmic equations have a restriction on domain because what's in the answer spot has to be positive. Just like roots, what's under the root has to be greater than or equal to 0. We don't use equal to 0 because we can never use an exponent to generate a 0. This is a 3rd domain rule that we are adding in. This is the last one, by the way. Okay, 3rd algebraic domain rule. So that's going to tell us domain. How about range? How far south, how far north? -infinity to infinity. Range. -infinity infinity to infinity. And what's the equation of the vertical asymptote? X equals what? -8. Don't forget, this is an equation. How do you feel? Good? So from this point forward, when I say, okay, domain algebraically, what are the 3 rules? Denominator, even root, is it logarithmic? Those are the 3 things we have to consider. Okay, now, what's the last question on your list that you have to find? The what? The x-intercept, correct? X-intercept. So here's our jog down memory lane again. What do we know about all x-intercepts? Y is going to be 0. So when I go to my equation up here, where do I substitute y? F of x. So I should write an equation down that says 0, which is my y value, is equal to log base 2 of x plus 8. You're going to say, great, I'm glad that I wrote that because I don't really get anything about logarithms. You're telling me the exponent of 2 is 0, that gives me x plus 8. What does that even mean? Well, let's translate it. What's the base? What's the exponent of 2? 0, right? 2 to the power, the exponent is 0, is equal to what? X plus 8. What's 2 to the 0? 1 is equal to x plus 8. We get x is equal to -7. Is that our x-intercept? Yes, this is how you calculate the x-intercept algebraically. Questions? I feel like I went really fast there. Question? We're all good? All right, so I'm going to say this. From here to here, I'm going to tell you to study this. You're going to need to refer back to it when you complete the homework problems on this. Okay, we're going to study that. All right, so let's do the last example together to cement this idea. Put it together. Oh, what is this? That looks completely different. It's not. What does ln mean? Means natural log or log base e of 2x, 2 minus x, plus 3 is equal to f of x. Okay. Well, we talked yesterday, log base e looks like all the other, or exponentials, right? Exponential e 0, 1. So log base e is going to still be 1, 0. Doesn't change, right? We've got all this in here and all this in here. Now, question for you. Did I ever ask you to graph in this section? Does it say graph anywhere? No. So let's go right to algebra rules. Let's go right to the questions that they're asking. What's the first thing that you want to find? The domain. Okay. Domain comes from the parentheses group. What's in the parentheses group? 2 minus x. So I'm going to take 2 minus x and set it greater than 0 because whatever is in that spot has to be positive. It can't equal 0. So now I get 2x is less than 2. Yes? X is less than 2. How do I write that as a domain? Well, all the numbers less than 2. Thank you. Negative infinity to 2. Perfect. All right, now let's talk about range. What do we know about all logarithmic functions' ranges? They are always negative infinity to infinity. Domain, range. Okay, last one is what? Vertical asymptote. Ooh, where's the vertical asymptote going to be? At 2, correct? Plus 2? take this and set it equal to 0, it'll tell you where it is. X equals 2. The other way you could look at it is if I rewrote this, it would be negative x plus 2. All right, next thing. Draw a line. How do we calculate the intercept? I substitute what? Okay, I'm looking for this. So I know that y has to be 0. So I say, okay, 0 is equal to ln of 2 minus x plus 3. Step number 1, move the 3 to the other side. Isolate the log. Step 2, what's the base? It's not 2. What's the base understood to be right here? E. So if I convert this, I get e to what power? E to the negative 3 is equal to 2 minus x. So I get x is equal to 2 minus e to the negative 3. What is that in your calculator? Negative 1.905? Like that?
Wait, 950.
950, that's
Yeah, that's it. I misread.
negative 1.95. Yes? Now, I'm going to ask you to do something. Yes. Did you not get that? From here? Over there?
Yeah.
Okay, I moved x to the left to make it positive, and then I took the e to the power and moved it to the right. You know what I mean? Like I just, like once I'm, like when I look at this, I see this as one person, 2 people, 3 people. So I always want positive x. So rather than doing division, I just take this person and move it to the other side, and then I take this person and move it to this side. That's where I get that. Now, yes sir. Which one? The whole. Okay, so if I have a 0 here, 0 is equal to ln of 2 minus x plus 3. Negative 3 is ln, and then I put in a little e, 2 minus x. And then I said e to the negative 3 is equal to 2 minus x. And then I said x is equal to 2 minus e to the negative 3. All right, now this is what I want you to do to make this last connection. In your calculator, I want you to type this in, the original function. And I want to know if what we are writing down matches to what that picture says. Put it in. Check your vertical asymptote. Check your domain, your range, and also do you have a matching intercept? Two minus e to the negative third.
I said e minus 2. Like, e to the negative 2 minus.
Right, so what I'm doing is I'm having you check this. There should be one other error that you might find.
That's
This is on purpose. This is to teach you how when you take your test and use your calculator to check what you're looking for. Any other mistakes that you see with our list? Put it in, y equals, let's go. Put it in, put it in, put it in. Anything else?
how is, am I getting a negative 3?
It's not. It's not. That's what we were just talking about. But this is the positive. Did you get positive 1.95? Yeah. Check your work. Go in and check it. Look at it. Okay. One of the things as I'm grading the last test that I'm seeing very clearly is there's this missing step of what you're writing down and what you're looking at, the analysis of those things. You can do the mechanical skills, you can put it in the calculator, but you're not connecting those two ideas. Okay, so here was a prime example of that, and as soon as I saw it, I would have normally not had you graph it, but I wanted you to see that you should use the calculator to check your values. You should look at it, and then the only other step you would have is, did I enter it wrong into the calculator? You know what I'm saying? So that's kind of where we want to start to be with this as we move forward.